Hello everybody, it's Mrs. Pound and we are studying Chapter 10 on Chemical Reactions and Equations from BJU Chemistry's 5th edition. Today we're starting a new chapter, so we're starting with section 10.1a on reactions and chemical equations. Our objectives for today's video will be to recognize observable macroscopic indicators of chemical changes and recognize the symbols used to write a chemical equation. Evidence of a chemical reaction. The first is production of a gas. As you have seen before, when you add baking soda to vinegar, you get lots of bubbling. So a gas is being released. Now you do have to be careful with these evidence of chemical reactions because sometimes it's not evidence of a chemical reaction, such as when you heat up water and it starts to boil. That is not a chemical reaction, even though there is a release of gas. That is just a physical change. Changes in color. Sometimes there is a color change, and color change is a physical property that we are looking at. So we'll be looking for color changes. Also, a change in energy, such as light is produced, like when you start a match and you're burning wood. Sound, you hear a sound like a pop or a bang. There's a temperature change. Either it gets really hot, or sometimes it's the opposite. The thing gets colder. And there's almost always an energy change that occurs because the reason things are reacting is to get to a lower energy level usually. So there usually is an energy change of some kind. Also, formation of a precipitate. And a precipitate is a solid that comes out of the solution when there is a reaction, such as in the picture in the background, this yellow precipitate has formed. We are going to be using chemical equations to represent chemical reactions. And a chemical equation is a model used to represent all the substances involved in a chemical reaction. It uses chemical formulas, chemical symbols, and coefficients. Now, chemical equations must identify all substances involved in the reaction. So we have to write everything down that we are using. They also must show the composition or formula of the substances involved. So we can't forget what we learned in the last chapter about writing formulas. We're going to be writing and practicing a lot of formulas still. Also, they must account for all atoms involved in the reaction because we have the law of conservation of matter, and so we have to keep all the matter the same. What goes into the equation must come out. Symbols used in chemical equations are the plus sign goes between reactants and between products on each sides of the arrow. There is an arrow sign, which means yields or produces, and it separates reactants from products. Reactants are on the left, products are on the right. Sometimes an equal sign is used, and it means the same as a single arrow, although this is not very common. Sometimes there's a double arrow, and this is used in the place of a single arrow for reversible reactions. These are reactions that can go both ways. Lowercase g indicates a gaseous reactant or product in parentheses, and a lot of times this will be hard for you to write, but a lot of times you'll see this in italics. An up arrow is sometimes used to indicate a gaseous product as well, but only products, not reactants. Lowercase s in parentheses indicates a solid reactant or product. A down arrow is also sometimes used to indicate a solid product, which is called a precipitate. An L in parentheses indicates a liquid reactant or product. And an AQ in parentheses indicates that the reactant or product is in an aqueous solution, which means that it is dissolved in water. A delta, which is a triangle over the arrow, indicates that heat must be supplied to reactants before a reaction occurs. It looks kind of like the flame at the top of your Bunsen burner. And an arrow with a chemical written over top of it, a formula, indicates that a catalyst must be supplied to reactants before a reaction occurs. And we'll talk about a catalyst in a minute. Now, usually the arrow goes the whole length under the catalyst, with the limitations of my being able to type this. It's a little short, so make your arrow long enough that it goes under the whole manganese oxide. Now, reactants are on the left side. These are elements or compounds that undergo chemical change, and these are on the left side of an arrow. Products are on the right side, and these are elements or compounds produced from a chemical reaction. So let's take a look at some of these reactions, how we write them. So a reversible reaction is a reaction that can occur in the reverse direction as well as the forward direction until equilibrium is reached. So an example of such a reaction is this. So we have 3Fe, which is iron, plus 4H2O, so that's 3 atoms of iron, reacts with 4 atoms of water to produce iron 4 oxide, Fe3O4, plus 4H2, so 4 molecules of hydrogen gas. So in this reaction, notice the reversible arrow. It is a reversible reaction. Sometimes a precipitate is formed. This is a solid that comes out of solution due to a chemical or physical change. So we're actually going to add some symbols to the previous equation. So my example would be 3Fe with an S in parentheses after it, plus 4H2O, which is a gas, in parentheses, reversible reaction, yields Fe3O4 solid, in parentheses, plus 4H2 gas, which the G is in parentheses. Or another way to write this is we could leave the beginning the same, but since the Fe3O4 is a precipitate, we can use a down arrow, and because the hydrogen gas is released, we can use an up arrow in the place of S and G. Another example using aqueous would be silver nitrate, which is aqueous, AQ in parentheses, plus sodium chloride, which is aqueous, AQ, yields silver chloride, which is a precipitate, so I use the down arrow, plus sodium nitrate, which is aqueous, so it's dissolved in water. Sometimes we use a catalyst. A catalyst is a substance that changes reaction rate without permanent change to itself. Many catalysts are used to start reactions because they lower what we call the activation energy. We don't need as much energy to get them going. So this might mean that normally we would have to heat it, but with a catalyst we wouldn't have to heat it to get the reaction started. So an example of a catalyst here is we have 2KClO3 as a solid. It's a reversible reaction, yields 2KCl solid plus 3O2 gas. So we see that. We could have also used an up arrow for the gas. Now over this symbol here, the reversible reaction symbol, we have Fe2O3 and the delta sign. So this requires a catalyst and heat. And again, make your arrows long enough that you can write that over the arrows and make it very clear that it's over those arrows because it's a catalyst and heat being used. Now you might be wondering why I'm putting these numbers out front here. If you've wondered that, the reason is because these are balanced equations. I'm going to show you in the next video how to balance an equation, but these numbers are out front because if we wrote it without the numbers, we would not have the same number of atoms on the left with the reactants as we would on the right with the products. So remember, left reactants, right products. What goes in must come out. So we have to put coefficients out front in order to adjust those. We cannot adjust the subscripts because that would then change the formulas and we would be representing a different compound. So our objectives for today's video to recognize observable macroscopic indicators of chemical changes and recognize the symbols used to write a chemical equation. In the next video, we will be learning how to balance those equations and put those coefficients out front. So don't forget your 5 questions in the margin, and I'll be back with more in the next video.